Okay, so as the last few people are coming in, let's go ahead and get started. Last week we looked at organizing data and grouping data and stuff like that and displaying it graphically. This week we're going to look at how do we describe it numerically. And so we talked about the whole idea of a distribution, and where we take a number line and we number our possible values across the number line, and we did the dot plot. Then we drew the curve over the top of those dots. And we said that most distributions have a shape similar to this one, that bell curve, or what is called a normal curve. Because in nature, that is the shape that most data normally takes. If you're looking at people's heights, they'll take that type of a shape, where most people have a height that's somewhere in the middle. If you get really tall, there's very few people that are really tall and very few people that are really short. Remember, the height of the curve tells us how many items take on that value. Well, as we go to describe this, we might have another curve that's identical in shape, but it might sit like this. The way we would describe the difference is the center of the curve is different. So the center, of course, is the middle, or where the peak of the curve is. So we need a way to describe the center, or how the center of two curves might be different. The other thing we might have is we might have a curve here. That green curve and the black curve have pretty much the same center, but the green curve is narrower. We would describe that as having less spread or dispersion. So our first step is to talk about numerically how do we come up with measures of center and spread. So we'll start out with measures of center. And actually, let's start out with a couple of data sets. I'm going to put some data sets up here. And let's see here. There's one, and I'm going to put a second one up here, so we'll do two examples of each of these. Okay, so for our first measure, we're talking about measures of spread here again, or not spread, measures of center here. Our first measure of center is the mean. The mean is what most of us have been taught through the years is just the average. So we add them up and divide by how many numbers are there. So now we have to define n, which is the number that's in each list. So there's 1, 2, 3, 4, 5 numbers in this list, so n equals 5 for that list. For this list, there's 6, so n equals 6. So n represents how many items are in the list. The mean is the total, that's the summation symbol, the total divided by n. So for this list, 8 plus 13 plus 15 plus 16 plus 23 divided by 5, because there's 5 numbers in the list. So what do we have there? 21, 36, 52, 75 divided by 5 gives us a mean of 15 for this first data set. For our second data set over here, same thing. 11 plus 27 plus 13 plus 24 plus 14 plus 16 divided by 6. So we have 38, 51, 75, 89, 105 divided by 6, which is what, 17.5 is our mean for that data set. So the mean, just the average that we've been calculating since about 3rd or 4th grade. The median, which is another one of our other major measures of center, is simply the middle number. Now to do the median, we have to do a couple of things. One, we have to put them in order. Now this first data set is already in order from smallest to largest. Second thing we have to do is we have to find the position of the median. Now the median is the middle number, but another definition is it's the number such that half the values are smaller and half are larger. So we want to find the halfway point. So to find the median, or find the position of the median, we use 1/2 or 0.5 times n. So for this set, it's 0.5 times 5, because there's 5 numbers in the list. Gives us 2.5. Whenever we have a decimal in this number, 0.5 would be our decimal, we round up. So it's going to be the third number in our list is going to be our median. So we look up here, the third number in our list is 15. So the median of that data set is 15. Over here now, we have to put them in order. I didn't put that data set in order. So it's 11, 13, 14, 16, 24, and 27. So that's step 1. Step 2, finding the position. Well, it's 0.5 times n is 6. That gives us 3. Over here, we had a decimal. We had 2.5, so we just rounded up to the next spot. When we have a whole number, it is between that one and the next. So that means that this is going to be between the third and fourth number in my list. So here's the third and here's the fourth. How do we find what's in between them? We're just going to add them together and divide by 2. 14 plus 16 is 30. Divided by 2 is 15. So I have a median of 15 there. Now you'll notice in this data set, my mean and median are exactly the same. In a good data set, well-distributed data set, the mean and median should be the same. Every measure of center should be the same. Over here, they're not very close to the same. That's because there's numbers here on the top side that are kind of spread out and pushed out. And we're going to look at that a little bit more in just a couple minutes. For now, I want to discuss some of our other measures of center. One is the mode. The mode is the number that appears most often. Now for small data sets like I have here, there isn't a mode very often, because not very often are there numbers that are repeated. So for these two data sets, there are no numbers that are repeated. So there is no mode for either one of these, because there's nothing that appears twice. As the data sets get larger, the mode becomes more useful because there are numbers that are repeated over and over again. Now there might be in a medium-sized data set, there might be 2 or 3 numbers that all appear twice. So is that no mode, or do we have multiple modes? And that depends on your textbook. There's different theories, different schools of thought in statistics. Some of them say there can be up to 2 modes. Others say that depends on the size of the data set. The bigger the data set, the more modes it can have. For our purposes in this class, either there is 1 or there is none. Now, of course, in these two data sets we had, there's no mode in either one because no number is repeated. But if you have a data set where there's 2 different numbers that appear twice, for this class, we're going to say that there is no mode. The final measure of center is something called the mid-range. Now, the mid-range is going to require us to define 2 other numbers, 2 other items. We have the minimum, which is the smallest number in the list, and the maximum, which is the largest number in the list. So looking here, for this set, we have 8 and 23 are our minimum and maximum. So our mid-range is 8 plus 23 divided by 2. We average the minimum and maximum. So that's 31 divided by 2 is 15.5. Come on. 15.5. Again, really close to the 15 that we had for both the mean and the median. For this second set here, our smallest number is 11 and largest is 27. We have 11 plus 27 divided by 2. 11 plus 27 is 38. Divided by 2 is 19. So you can see that one's different yet. For that data set, the numbers are quite spread out. For our different measures of center are quite spread out. This data set here forms a relatively decent bell curve. It's a good data set. This data set here is what we call skewed. It's stretched out like this to the right. That's why the median, mean, mid-range are all different. So the question is, which measure of center is best? Now the mid-range we saw is quick, but only involves two numbers. The mode, we saw how unreliable that is. We didn't even have a mode. So we're basically narrowing it down to the mean versus the median. And for most people, they look at that mean and say, hey, we're running numbers into a formula. We're adding them together, we're dividing it out, we're cranking through. It feels like we're doing something important there. So for most people, the mean feels like it's a best measure of center because we've got the formula, the average. And we've seen it since we were very young. But we look up here, we see that the mean and the median were quite different in this set. Here they're pretty much the same, so it really doesn't matter which one we use. Which one of these is a better description for this data set? Let's take a look at another data set just to give you an idea. So I'm actually going to do two data sets here, and I'm going to put them in order from smallest to largest just to make it easier on us. So here's my first data set. Let's find our mean and our median. So our mean, we're just going to add them up. I'm just going to do that right here. 18, 41, 65, 92, 125. So it's 125 divided by 5, which is going to be 25. There's our mean. Our median, well, 0.5 times 5 is 2.5, which tells us that it's the third number in the list. That's going to be the 24. So we get a mean of 25 and a median of 24. Let's take a look at a second set of numbers here. Looking at that, looks kind of familiar, hopefully. I'm just adding one number to it, 67. So now when we go to find our mean, this is going to be 192 over 6, which is a mean of 32. Our median, well, it's 0.5 times 6, which is 3. So that's telling us it's between the third and fourth. Remember, if it's a whole number, it's between that one and the next position. So it's between the 24 and 27. 24 plus 27 is 51 divided by 2 is 25.5. So if you look at this, what happened here, you see our median went from 24 to 25.5, a small change. But the mean jumped from 25 all the way up to 32. Now 32 falls in here. The 33 is just barely larger than that. I would not say that that's a good measure of center. There's 4 numbers here smaller than it, and it's really close to this next one. Whereas for the median, it's right here. There's 3 smaller and there's 3 larger. It's still in the center of the data. The median is what we call more stable. Those really large numbers or really small numbers don't affect it as much. Those really large and really small numbers are what we call outliers. And when we're doing research, one of the things we have to do is we have to look for those outliers. And we have to decide whether they're going to stay in the data, whether they're a legitimate part of the data, or something we need to take out. It's possible that there is just a number out there that's way bigger than the rest or way smaller than the rest. So we have to keep it in our data set. But there are other times where we might realize it's a measurement error. We measured something incorrectly, and that's not really a legitimate data point. So then we have to make sure we take it out so it doesn't mess up our data. In medical research, this happens a lot. We've talked a little bit about drug testing and how that's a big application in medical research. In drug testing, there's always several patients, several items in our sample that are not included in the final analysis. Let's say we're testing a new medication, and we have someone who, let's say we're testing a cancer treatment, and we have a patient who dies of cancer, who dies of a heart attack halfway through the trial. Well, their cause of death was not what they were being treated for, not what the medication was for. So their results, unless they can show that the heart attack was caused by the medication itself, their results are not relevant to that trial. So their information is removed. Now, it's always duly noted somewhere in the final report who was removed and why. So it has to be noted that this one was removed as an outlier because, and it has to be justified. But those patients are always removed because it's not necessarily relevant to the medication what happened to them. Something outside of the control of the experiment happened, so we don't include them. Let me give you an example of this outliers and what an effect it can have. In 1983, University of Virginia advertised that the average starting salary of someone who graduated from their bachelor's degree in marketing that year was just under $78,000 that year. Now you look at that right now, if you could come out of college making $78,000 a year, that's doing really well. Back in 1983, if you look back at the numbers, the average high school teacher was starting out at between $16,000 and $18,000. So $78,000 looks even better for 1983. Well, there's a problem here. One of the graduates in their marketing program that year, who did graduate with a marketing degree, was a man by the name of Ralph Sampson. Now, I realize none of you are old enough to remember, but Mr. Sampson was 7 foot 4 inches tall, was 3-time NCAA basketball player of the year. Was drafted number 1 by the Houston Rockets. Now, back in 1983, again, athletes weren't making the $20-30 million a year they are in some places now, but basketball was still the highest paid professional sport. So Mr. Sampson still signed a multi-million-dollar contract. It takes a lot of $20,000 a year marketing graduates to average one multi-million-dollar player down to $78,000 a year. In fact, Mr. Sampson was the only player, or the only graduate in the marketing program that made more than $33,000 that year. The median was just under $22,000. So you can see there how unstable that mean is. This also illustrates our outliers. In this case, the pay for Mr. Sampson had absolutely nothing to do with being a graduate in the marketing program. Therefore, including his pay in the average really didn't have any meaning to the results. They just included it because it made their school look really good, which I can't blame them for that. But if you want to get into the ethics of it, it probably was not an ethical move. Okay, so those are our measures of center. The next thing we want to get into now are those measures of spread or dispersion. So to talk about measures of spread, I'm going to put a couple of data sets up here. So there's one. And here's the second one. Is that one going to work? Yeah, we'll make it work. Okay. So if we look at these, one of our measures of spread is to just use the range. The range is simply the maximum minus the minimum. So for this set here, the maximum is 25, the largest number. The minimum is the smallest number is 11, gives us a range of 14. For this one here, the maximum is 25, the minimum is 11. We also get a range of 14. But if you look at this, I would argue that this set is more spread out than this one. So the range does not do a very good job of distinguishing between those two. A better measure of spread is the standard deviation and the variance. Standard deviation and variance are very closely linked together because the variance is just one step before getting the complete standard deviation. Rather than giving you the long formula for this, I am actually just going to go ahead and, it's a 6-step calculation process, so I'm just going to go ahead and go through the 6 steps of the calculation with you. Step 1 is to find the mean. So we're going to go ahead and use this data set here first. So 11 plus 14 plus 16 plus 19 plus 25 divided by 5. So it's 25, 41, 60, 85 divided by 5 is 17. So we got a mean of 17. Step 2 is to subtract the mean from each. So we have 11, 14, 16, 19, and 25. And we are going to subtract 17 from each. So 11 minus 17 is a negative 6. 14 minus 17 is a negative 3. 16 minus 17 is a negative 1. 19 minus 17 is a positive 2. And 25 minus 17 is 8. Now, it doesn't have much meaning at this point, but we can double check this by adding this up. That should all add up to 0 at this point. Now, that 0 doesn't mean anything. It's just a double check to make sure we haven't made any bad mistakes. Step 3 is to square each of these. So negative 6 squared. Make sure you put it in parentheses, because if you don't, your calculator is going to try to tell you it's a negative 36. But remember, anytime you square a number, it has to be positive. So that is a positive 36. Negative 3 squared is a positive 9. Negative 1 squared is a positive 1. 2 squared is 4. And 8 squared is 64. Next, step 4 is to find the sum of those numbers. So we got 36, 45, 46, 50, 114 is our sum. Step 5. We're going to divide by n minus 1. So for this data set, n equals 5. So that means we're going to divide by 4. So that gives us 28.5. This number here would be what is called the variance. If we get into in-depth statistical analysis, hypothesis testing, and stuff like that, the variance becomes a very important number. At the basic level, however, it really isn't used that much. What we're more concerned with is something called the standard deviation, which is step 6, square root. So it's the square root of 28.5. Which gives us 5.34. Unless you're told otherwise, go to 2 decimal places on a standard deviation. I think on the test I asked you to go to the nearest 10, so it'd be 1 decimal place. But, you know, that is the standard deviation. And what that tells us is, on average, how far is each data point away from the mean? Now let's quickly go through this other data set here, the 11, 16, 17, 18, 25. First thing I need to do is find the mean. Well, let's see, I've got 27, 34, 52. 77 divided by 5 is 15.4. So I'm going to subtract. 15.4 doesn't look right. 15.4. Let me try that again. Something must have added up wrong. So I've got 27, 44, 62. That should be 87. So that would make this 17.4 subtracted from each. So this is going to be a negative 6.4, negative 1.4, negative 0.4, 0.6, and 7.6. And we would have to square each of those. Now at this point, for the sake of time, since we are at 12:07, you're only got a little over 10 minutes left. I'm going to leave it up to you to go ahead and find that standard deviation. I'll show you quickly what it comes out to be. I put in 11, 16, 17, 18, and 25. The standard deviation there comes out to be 4.50. So you can see that comes out to be a smaller number than what we had here, the 5.34. And we did say that this data set felt less spread out. So the standard deviation does a good job of distinguishing between the spread of those two data sets, where our range did not do a very good job. Okay, moving on. Next thing I want to address is what are these used for? What good does the center and spread do us? I want to talk about something called the empirical rule. And the empirical rule talks about if we have items that are approximately normally distributed, approximately a normal curve, like most items in nature are, we can come up with some basic ideas of where the numbers should be. Now I'm just going to draw out a bell curve, or as close to a bell curve as I can come here. And what the empirical rule says is the middle of that bell curve should be the mean. And if we go out from that bell curve using steps that are equal to a standard deviation. So this spot right here would be 1 standard deviation below the mean. So I'm going to write it as -1 standard deviations. 34% of the data, approximately 34%. Your textbook actually uses what they call the exact or detailed empirical rule. If you want to use those numbers, that's fine. I use what's called the approximate empirical rule just because it's easier, it's quicker, and it's close enough. It's all of them are estimates. So approximately 34% of the data will have values between the mean and 1 standard deviation below the mean. And approximately 34% will be between the mean and 1 standard deviation above the mean. If we go 2 standard deviations below or above, between 1 and 2 standard deviations from the mean, approximately 13.5% of the data will be. And then between 2 and 3, approximately 2.35% of the data will fall in that range. Then outside of 3 standard deviations in either direction, it's only about 0.15% of the data. But what does this mean? Well, let's say that on a certain test that I give, there is a mean score of 82 with a standard deviation of 6. On this curve, the 82 would go in the center. And then we would go up or down by 6, by the amount of the standard deviation in each direction. So subtracting 6, this would be 76, 70, and 64. Adding 6, this would be 88, 94, and 100. So on average, we'd be looking at the scores being distributed like this. So somebody who scores an 88, you look at 88, you look at this and say, hey, historically, if I add up those percents, I get 84%. Historically, 84% score less than 88. Now, of course, I can look at the other side and add those up. That comes up to be 16%. 16% score more than 88. Let's say you had a bad day and you scored a 70. So here's 70. If you look at that, you look at these here, you add up those percents, you get only 2.5%. So that's telling you that, hey, historically only 2.5% score lower than that 70. So it's a grade you'd want to improve on. This can be used for comparing a lot of things. For example, let's say you get out of school and you get your first job and you're looking to buy a house in the area of your job. You want to buy a 3-bedroom, 2-bath house. So you look up, you do some research in that area, and you find that in the area that you are going to be buying that house in, the mean selling price for 3-bedroom, 2-bath houses is $112,000. The standard deviation is $24,000. So you are looking for a house and you find one that you absolutely love, and it is priced at $160,000. And your retailer is, your realtor is telling you you need to put in an offer on this house right now or it's going to be gone. Well, to analyze this, we can go back to this bell curve and the empirical rule. These percents in here will always be the same. Again, depending on which version you use, your textbook has a little bit different percents, but they're pretty much the same. So anyway, the center of this is going to be the mean. Our mean was 112,000. So I'm just going to write 112. The standard deviation is 24, so we go up or down by 24,000 at each step. So subtracting 24 here would be 88,000. Subtracting another 24 would be 64,000 and 40,000. Going up by 24, 136, 160, and 184,000. So what does this tell us about the house you're looking at? Well, it's 160,000 right here. If we look at this, if we add up these percents here, that tells us that 97.5% of all 3-bedroom, 2-bathroom houses in that area are cheaper than the one that you're looking at. So that's telling you that either you can put in a lower offer or you just pass on that house and there's a good chance you can find one that's cheaper that you'll like. Okay, the next thing, the empirical rule works well if the numbers are right at one of these steps. But if it's in between, it doesn't work so well. And there is something called normal probabilities that we don't have time to get into in this class that allow us to calculate for exact numbers in between. We're not going to get into that. But if you were to go into a full-blown statistics course, you would calculate actual exact normal probabilities instead of these approximations. It's a great way of comparing things. Now, these normal curves are also a way that allow us to compare things from different populations. For example, let's say that you are taking your tests for college admission, and you take an English test and a math test. And on your English test, you score a 28, and on your math test, you score a 22. Well, there's a tool called a z-score that allows us to compare items that come from different populations. I mean, you might be tempted to look at this and say, hey, 28's bigger than 22, you did better on the English test. But you don't know for sure. Maybe the math test is a more difficult test. The z-score involves us taking a number, and from that number we subtract the mean for that population. Then we divide that difference by the standard deviation. So we need to know some more information to do anything with these. Let's say that on the English test, the mean score for all students who took that test is 22. And there's a standard deviation of 3. For the math test, let's say that there is a mean score of 17, a standard deviation of 2. Now you still might be tempted to look at this and say, hey, 6 points above the mean on the English test, only 5 points above the mean on the math test. Still looking like the English test is pretty good. Let's do the z-score. So here you had a 28 minus the mean of 22. And we'll divide by the standard deviation of 3. So 28 minus 22 is 6. Divided by 3 is 2. That z-score of 2 is telling us that that score of 28 is 2 standard deviations above the mean. Over here we get a z-score. Our score is 22 minus the mean is 17 divided by the standard deviation of 2. 22 divided by 17 is 5. Divided by 2 is 2.5. Got a z-score of 2.5, which is telling us on the math test you were 2.5 standard deviations above the mean. This is a more impressive score compared to the whole population that took that test. Another way of looking at it, let's say that you get a job as a manager in a retail store, and you have to fire one of your salespeople. And let's say you've got it narrowed down to 2, and you decide between person A and person B, whoever has the worst week this week is the one that's going to go. Well, person A works in electronics. And this week they have sales of $2,800. Person B works in toys, and this next week they have sales of $1,200. Doesn't look good for person B at this point. But again, electronics tend to be more expensive than toys, You've got to even it out by comparing them back to their own population. So let's say of all salespeople in electronics, the mean sales was 3,800 with a standard deviation of $300. Let's say for toys, the mean sales was 1,800 with a standard deviation of $200. Let's find z-scores. So the z-score here is 2,800 minus 3,800 over 300. 2,800 minus 3,800 is a negative 1,000. Divided by 300 is a negative 3.33. Now the negative is telling us that they are below the mean. So they are 3.33 standard deviations below the mean. Over here, z-score, 1,200 minus the mean of 1,800 divided by 200. 1,200 minus 1,800 is a negative 600. Divided by 200 is negative 3. That person is 3 standard deviations below the mean. The person in electronics, compared to the rest of the group in that department, did worse. So that would be the one that you would let go. Okay, we've got about a minute and a half left here, so before I lose you, let's go ahead and put some homework up here. We have page 347 through 348, 1 through 9 the odd. We also have page 353 through 354, 1 through 7 the odd. And finally, for our measures of spread, page 357 through 358, 1 through 6. So we've learned our measures of center and spread, and we learned z-scores, an empirical rule for comparing within our distributions, and then from one population to another we can compare. Wednesday we're going to look at what happens if this data is grouped. We had those frequency tables from last week. What happens if our data is set up in a frequency table? In other words, can we efficiently work with a larger set of data? How would we calculate some of these things from it? And then we'll start a little bit on probability, and we'll finish up probability on Friday. And then, of course, next week, Monday, is our unit test on statistics. Okay, you guys have a great day, and we'll see you on Wednesday.